So we're asked to determine the graph of f of x when f of x equals the natural log x squared times x. Now, in order to do this, we have to determine a few things. Okay, the first thing we're going to determine is our roots on this equation. Okay, so where does f of x equal 0? It's usually where you want to start with. So let's have 0 equaling ln x squared times x. Now, if we can break these things up, we are asking simply, where does x equal 0? And where does the natural log x squared equal 0? Well, x equals 0 when x equals 0, so that's nice and easy. And then here we are going to take x squared and make it e to the power of 0, because remember, that's what the natural log is. It's e. So now we have x squared equals e to the power of 0. And then anything to the power of 0 is 1. We're going to introduce a square root symbol, and remember, anytime you introduce a square root symbol, you have to take the positive and negative value. So x equals positive and negative 1. Now, before we move forward, we have to ask ourselves, are there any restrictions that x cannot be? Well, remember, inside any type of log, this cannot be negative or 0. Okay? The first thing you really want to notice is the fact that this thing is squared. Since it is squared, any type of number you put in there, it's going to give a positive number as a result, right? Even if we put -4 inside that x value, we will pop out with positive 16. Now, one thing to notice is we cannot put 0 in here. So x squared cannot equal 0. So simply x cannot equal 0. So that is a restriction we have to take into account. The reason I mention this is because this point here, 0, 0, this is a hole, okay? Because it does not fit in that restriction we just found. So that means if we start to try and roughly graph this, we know we have a hole at 0, 0, and then at +1 and at -1, we have 2 roots. So we're already a little bit on our way to graph this function. Now we have to find the maximum and minimum values. In order to find the maximum and minimum values of this equation, we have to find our first derivative. So let's start finding our first derivative of f of x equaling the natural log x squared times x. Now, a few things we have to notice here. We're going to have to apply the product rule because we have two functions multiplying each other. Another thing we have to recognize is when we derive ln x squared, we're going to have to apply the chain rule. Remember, the derivative of the natural log x equals 1 over x. Now, if you have something inside there, you're going to have to apply a chain rule. So let's say we have a function inside there. We will have to put this on the bottom. So the derivative is 1 over f of x times the derivative of f of x. We've just applied the chain rule to a natural log function with a function inside of our natural log. So let's begin. The first derivative in this case, well, let's first derive the natural log x squared. That will be 1 over x squared times 2x. 2x is the derivative of x squared, and then this is because of that natural log. Okay, and then I'm going to multiply it simply by x. Okay, so I got that. From there, I'm applying the product rule. Now I'm going to add the natural log of x squared and multiply it by the derivative of x, which is simply 1. From here, we can clean up our first derivative a little bit. So the derivative is equal to, notice we have 2 x's on the numerator and 2 x's in the denominator. So these nicely cancel out. So we are left with 2 plus the natural log x squared. Recall that we have to find the critical values in order to determine whether they are maximum and minimum points. These occur where the first derivative either does not exist or the first derivative equals 0. I didn't mean to make this a capital F. Sorry about that. So recognize these are not automatically max or min values. They're possibilities of being max or min values. So the first thing, where does the first derivative not exist? We'll recognize we still have that restriction, okay? So the first derivative does not exist when x equals 0, okay? So this is a non-permissible value in this case. Now, how about where does the first derivative equal 0? Well, we can find that by simply putting the first derivative to equal 0, equaling 2 plus ln x squared. And now we can solve for x. So subtract 2 by both sides. Remember, this is the base of e. So we can bring this and make -2 our power. So e to the -2 equals x squared. It's really important to be comfortable with what you're doing in terms of all of the different types of exponent and log rules you're going to be doing. I want to make this a positive value before I do anything. So I'm going to make it 1 over e squared equals x squared. Now lastly, I'm going to square root both sides. And remember, when you square root both sides, you have to take a positive and negative value. So here, I will get the positive and negative value of square root 1 over the square root of e squared equaling x. The square root of 1 is simply 1, and the square root of e squared is simply e. So we have two roots for our first derivative, which is a possible max or min value on our original function. How do we determine if that's a max or min value? Well, we have to use a table. Remember, in our table, we're going to also include where it does not exist. Okay, so we are going to have intervals set up where we're going to figure out what our first derivative is doing when x is less than 1 over negative e. We're also going to find when x is between -1 over e and 0, then when x is between 0 and -1 over e, and then when x is greater than 0. And again, we're finding out the increase and decreasing intervals here. In this case, for our first derivative, it's just one long expression, 2 plus ln x squared. So now we plug in our test values. So for here, we could use something obnoxious like -100. If we plug in -100 there, okay, recognize that our negative value is going to get canceled out and it'll simply be positive. Okay, it's going to be a very big positive number, which is going to make the whole thing positive. So that means when x is less than 1 over negative e, your original function is increasing. How about when it's between -1 over e and 0? Okay, well, when that is occurring, let's choose some value here. Okay, something to note, -1 over e, if you plug that in your calculator, if you just want to know roughly what that equals, sorry, let me just plug this into my calculator here. That equals roughly -0.367. So let's plug in something a little bit smaller. Well, I guess technically bigger than that. So let's do something like -0.25. Okay, so you could plug this into your calculator if you have like a mechanical calculator, and you are going to get a negative value. So this is an decreasing interval. Now, how about when you plug in between 0? This should actually be a positive e. I seem to have set these up incorrectly. And then positive 1 over e. So hopefully you saw that even when I wrote that out. Okay, I did my intervals a little incorrectly. Now I could plug in e equaling positive 0.25 and just recognize this is going to be actually the same value. Okay, so we're going to end up getting the same value of a negative solution here. So we're also still decreasing. Now finally, choosing some number that is bigger than 1 over e. So this time we could just do something like positive 100 and you'll get a positive interval. So what does this all mean? Well, this means if we draw out a line graph here, and let's plot negative 1 over e, 0, and positive 1 over e, when your x value is less than 1 over e, you're increasing. When your x value is between negative 1 over e and 0, you're decreasing. And that's the same for when x is between 0 and 1 over e. You're also decreasing. And then on our x value is greater than 1 over e, you're increasing. So here we have a candidate for a max point, and here we have a candidate for a min point on our original function. So how do we determine those? Well, we want to plug those x values into our original function. So let's find our max point. So our max point is at x equaling negative 1 over e. Okay, so our original function, if we can remember all the way back there, is ln x squared times x. So f at negative 1 over e equals ln negative 1 over e squared times x, which is negative 1 over e. Okay, so what's happening here? Well, we can do a few things to deal with this kind of mumbo jumbo. Let's apply this x squared inside, and it'll also get rid of our negative value. So ln 1 over e squared times negative 1 over e. Now at this point, this square value I could have actually taken out as well, which I probably will do. So this square value can be taken out, and I'm going to get 2 times ln 1 over e times negative 1 over e. Now, what does ln 1 over e equal? Well, remember, e to the power of what equals 1 over e? Or, yeah, so e to the power of what? Well, this would have to be negative 1, which makes this entire thing negative 1. So we have 2 times negative 1 times negative 1 over e. So we are going to get 2 times these two negatives will cancel out, 1 over e. So our max value is going to be found at negative 1 over e and 2 over e. So we can go plot that roughly. Okay, so if we plot that, we will have 2 over e up here, and it's going to be plotted somewhere around here. Okay, now how about our min point? Remember, our min point is at when x equals positive 1 over e. So again, we just have to figure out what the y value is when x is 1 over e in our original function. So let's plug that in. 1 over e equals ln 1 over e squared times 1 over e. I'm going to actually take this squared out immediately. So I'm going to get 2 ln 1 over e times 1 over e. We just discussed how this is equal to positive 1, or sorry, negative 1. So we get 2 times negative 1 times 1 over e, which equals negative 2 over e. So now we have a min point at positive 1 over e and negative 2 over e. So we can roughly graph that. So somewhere here, negative 2 over e, we're going to get down here. Okay, so we have found our max and our min points. Let's now focus on inflection points and concavity. So remember, concavity and inflection points are tied to the third derivative. They show us whether we should be concave up, concave down, and where we have a change in concavity. So our second derivative is the derivative of our first derivative. Our first derivative we've found to be, where is our first derivative? 2 plus ln x squared. Well, to derive this, it's actually quite a bit easier than before. The derivative of a constant is 0, and then here we'll have to apply our natural log derivative rule and then our chain rule. So let's derive ln x squared, which is 1 over x squared, and then derive the inside, which is x squared. The derivative of x squared is 2x. So the double derivative, or the second derivative, we can cancel out an x and get positive 2 over x. Now, inflection points are quite similar to trying to find max or min values. They can either be tied to when the second derivative does not exist or the second derivative equals 0. Hopefully you notice that this can never equal 0, but it has a non-permissible value where x cannot equal 0. So this is making your first derivative not existing. So now we have a crit value and a possible value for an inflection point. So let's create a table and figure out where you have concave down intervals and concave up intervals. So here we'll have 2, I'll break it into its components of 2 and 1 over x. My intervals here will be when x is less than 0 and then when x is greater than 0. Now at this point, both these will be positive no matter what x is. 2 is always positive 2. When you have a x value less than 0, so possibly x equaling -10, well, this will be a negative value. So this makes it concave down on the interval here. Okay, so I usually either put CD or a concave down rough graph. Now what happens when x is greater than 0? Well, again, x equaling +10 this time, well, that will make it 1 over 10, which is a positive number. So here we have concave up, so it'll be roughly like that. So that means if you were to draw a number line to represent this at 0, you have concave down on this side and then concave up here. Here you have an inflection point. Even though it's a hole, it also is an inflection point. Okay, so on our original graph, if we come up here, we can kind of tie everything together. Remember, for our decreasing/increasing intervals, we have our points -1, +1, and 0. And if we were talking about our decreasing and increasing intervals, it's going up, down, down, up. Okay, and then we have our min value and our max values, which we've already plotted. If we want to talk about our concavity intervals, well, when we are less than 0, we're concave down, and then when we are greater than 0, we're concave up. So we can tie all of this together with this understanding. So at this point, I'm noticing here when I graph these, this should be graphed at our values here is -1 over e 2e. So this should be -1 over e. This should be +1 over e, and we get it here. Okay, sorry about that. So when we graph these, now we can put everything together. okay? So we are increasing and we're concave down. So we're increasing here, go through our root, we come to the top. Now we're going to decrease, but we're still concave down. So I'm going to try and draw concave down as best as I can. We go through our hole, and at this point, now we are concave up. We go to our minimum, and then we come up. So this is roughly what our graph looks like. And then we would be done, okay? If we really wanted to, we could graph this and check our solution. So I have graphed here our function, and I have plotted our 2 points, which are here and here, and then our hole. If you see, we have been able to actually graph this pretty well compared to what we did over here.